We are going to do some more questions on equilibrium constant. This is the case, we call it as small k. Small k means the value of equilibrium constant is less than or equal to 10 to the power of negative 4. So what I actually mean by this, the reaction is more towards the reactant and very less amount of product is formed. So in order to explain this, just consider one example, A plus 2B giving you C, and let's just assume the concentration of A is 5, concentration of B is 10, and let the equilibrium constant for this reaction is 10 to the power of negative 5. Using the ICE techniques, get the equilibrium concentration and substitute it into the equilibrium equation. And as I said, this is the case in which the equilibrium is shifted more towards the reactant or very less product is formed. That means the value of X is very small, or in other words, X is much less than 5 for A and the concentration of A, and X is very much less than 10, the concentration of B. And therefore this equation is then approximated to 10 to the power of negative 5 equals X divided by 5 times 10. And that gives me the value of X as 5 times 10 to the power of negative 4, and it clearly indicates that the value of X is very low. So as per our assumption. So we will do some more questions on this small k equilibrium constant. We will do the first question on small k. Calculate the equilibrium concentration of C for a reaction with an equilibrium constant of 4.2 10 to the power of negative 10. We started the reaction with 22.5 molar of A and 15.6 m of B. So looking at the equilibrium constant, you know that it is a small k question. And the equation given is 2A plus B giving you 2C. And the equilibrium constant expression is written there, 4.2 times 10 to the power of negative 10, C square divided by A square B. And this is, please make a note that this is a small k. So using the ICE technique, with the initial concentration of 22.5 and 15.6, calculate the equilibrium concentration of A, B and C. Substitute it into the equation. When you do that, you realize you can apply the small k approximation. 22.5 and X, if you compare, X is much smaller than 22.5. Same way, X is much smaller than 15.6, and hence the equation reduces to 4.2 10 to the power of negative 10 equals 2x to the power 2 divided by 22.5 and 15.6, and the value of X comes to 9.09 10 to the power of negative 6, and the concentration of C is twice of X, and that's equal to 1.81 10 to the power of negative 5 molar. See, the small k approximation makes it easier to solve this question. Otherwise, this will be as a question in which X will be to the power of 3. Calculate the equilibrium partial pressures of A, B and C. The equilibrium constant for the reaction is 5.62 10 to the power of negative 9 at 300 degrees Celsius. The reaction was started with pure A at 0.852 atmosphere, and the reaction given is 2A giving you B plus 2C, and again this is a small k problem, and since all pressures are given, the value of Kp is written there, and then using the ICE technique, calculate all the equilibrium partial pressure and substitute it into the Kp equation, and do the small k approximation that X is very small, and hence I get the value of X as 1.01 10 to the power of negative 3, and with the value of X I can get the all the partial pressures of PA, PB and PC, and you can see that the partial pressure of A hasn't changed much. It's changed by just 0.001 unit. Let's do one more question on this small k. 0.60 moles of nitrogen gas is mixed with 0.96 moles of oxygen gas in a 4-liter container at 1000 K. Calculate the equilibrium concentrations of NO, and K is given. So again, this is a small k question. And as you can see that concentration is not directly given, moles and volume is given. Therefore, calculate the concentrations. Moles over volume will give me the concentrations. And then afterwards, again use the ICE technique, get the equilibrium concentration, substitute it into the equilibrium equation. And let's do the small k approximation, like that x is small. And I get the value of x as 6.9 10 to the power of negative 4. And the equilibrium concentration of each one of them can be calculated. NO is, no, they've asked the equilibrium concentration only for NO. Therefore, equilibrium concentration of NO is twice x, and that comes to 1.4 10 to the power of negative 3.